Continuing with the second part of this lecture 2, uh, the structure of graphite, as I mentioned, is uh, it has very high strength in the direction of the carbon bonds, but between those layers, it does not have as high a strength. So it's all held together by just by van der Waals bonding. So these layers are pretty weak between the layers, but in the layer itself, it is pretty strong. So how do you make um, carbon fibers out of a precursor such as polyacrylonitrile, that is petroleum based? So this precursor is dissolved in a solution, and it is pulled through a number of dyes. And so typical numbers are like 1,000 filaments, and those filaments are first oxidized up to 250 degrees centigrade in air. It stabilizes the carbon structure. Up to 250, up to 400 degrees centigrade, carbon does not burn, so it is pretty strong. But after that, you it is carbonized between 250 to approximately 1200, 1500, 1200 to 1500 degrees centigrade. During that time, it removes the nitrogen, carbon dioxide, carbon monoxide, hydrogen, nitrogen, and organics, etc. And so now you get an absolutely pure form of carbon. And then, if you want really organized carbon layers, then it is graphitized between 1500 to 250 to 2500 degrees centigrade for a very short time. It could be like maybe like an hour or so, and as it comes out, you can, I mean, by modifying this process, you can get different forms of the carbon fiber, either high modulus or high strength carbon fibers. So when you look at the structure of the polyacrylonitrile molecule itself, it has got several carbon bonds which are not filled completely, which is in the flexible form, and it has got triple bonds of carbon, nitrogen, etc. If you are taking the cyclic or rigid ladder molecule of polyacrylonitrile, it has got those benzene rings, and also the nitrogen bonds in double bonds with the carbon. So what happens when you are heat treating this polyacrylonitrile at under tension at different temperatures? So the tensile strength goes up if your heat treatment is limited to approximately 1600 degrees centigrade. Young's modulus keeps going up when you uh, up to 2600 degrees centigrade or so. So you get the highest modulus for the highest heat treatment temperatures, but the strength actually goes up and then it starts coming down. So now you know how to tailor the properties of the carbon fibers according to what you need. So if you limit your heat treatment temperature to around 1600 degrees centigrade, you get highest strength but low modulus fibers. Not, I mean, low in the sense it's not the highest case. But if you graphitize to the maximum temperature possible, you get the highest modulus but reasonably high strength. And now there are other techniques that people are using nowadays in order to get really high strength and high modulus carbon fibers, that is based on carbon nanotubes. So you pull the carbon nanotubes, and as soon as you are pulling it and graphitizing it, you get really high strength and modulus at the same time, but they are more expensive, obviously. You can also produce carbon fibers from cellulose. So these are rayon precursors, based on rayon precursors, and these are the kinds of fibers that used to be used for uh, for rocket casings and things, I mean rocket nozzles and things like that. You can also make lower cost fibers. In fact, there is a company called Zoltec that makes these fibers out of pitch-based precursors, and they claim, I don't know how far it is true, they claim that these carbon fibers are approximately $5 a pound, whereas the polyacrylonitrile can be as much as about $60 a pound. So that's the kind of difference you can have. But what is the problem with pitch-based fibers? They contain a lot of nasty stuff, uh, sulfur, arsenic, etc., from the bottom of the barrel, and sometimes you can't even ensure that the properties are consistent. So this is what you would find on the, if you took a look at the scanning electron microscope of a one single carbon fiber. So you can see the striations on the carbon fiber, and in this case the fiber diameter is approximately 8 microns. Nowadays you are getting even 5 microns or lesser type of carbon fibers. And the smaller the carbon fibers, the higher the strength, the higher modulus. So how can you represent this carbon fiber in 2D form? So these are the undulating graphitic ribbons, and they are rolled together in like a paper form. So, and this is one part of the carbon fiber itself. And it is completely rolled up like this. So you have multiple layers of these graphitic rings that are held together in a rolled up paper form. And the more the orientation which happens, the higher the heat treatment temperature. So when you do that, the modulus of these fibers really goes up. And it also depends upon the type of precursor that you are using. So actually you can get the highest graphitization with pitch-based fibers, because pitch is one of the purest forms of carbon. So you can see that the more the orientation, the higher the modulus. And how do you look at the properties? I mean, what are you really looking for in the carbon fibers? So if you look at the oxidation resistance of the fibers as a function of temperature. So if you have low modulus carbon fibers, they undergo considerable weight loss percent as a function of the starting weight. And so this means that the low modulus carbon fibers are not very good for the as an oxidation resistant carbon fiber. So the higher modulus fibers, carbon fibers are, I mean, they do not lose as much weight percent, and they retain their properties as a function of temperature and number of hours. You can also have other types of fibers based on other types of precursors, and there has been a lot of work that has taken place in the last 40-50 years aimed at making very strong and stiff synthetic polymer fibers as reinforcements. And, and the reason is that in the early 90s, when Boeing was really looking at making their composites for airplanes and commercial aircraft, etc., using carbon fibers. One of the issues that they found was that there was a question about the supply of carbon fibers. So it was always a problem. So people started trying to develop other types of fibers. But fortunately or unfortunately, carbon fibers are the best in the business. And however you might try, you're never going to get the kind of properties and the weight savings from other types of fibers. You may find that in the case of Kevlar fibers, but you can't put Kevlar fibers around the whole aircraft fuselage. So it has to be carbon fibers. So how do you make these fibers? Fibers are made by a process. You can have um, wet spinning or dry spinning or whatever. So basically they all have to be spun where you are extruding a liquid through small holes in a spinneret to form solid filaments. And the starting material is either a polymer melt or solution, and those filaments will emerge out of the holes in a spinneret, pass through a bath and an oven before being wound on some kind of a spinneret or a bobbin, just like a a sewing machine. So you can have melt spinning, dry spinning, wet spinning, etc. So these are the different variations of that process. So what kind of polymer fibers are present? First of all is the polyethylene. Polyethylene linear molecule, or you can have aramid. And there are two radically different routes for obtaining these structures: gel spinning for polyethylene and liquid crystal route for aramid. So in the case of polyethylene, it's a linear thermoplastic, so you can heat it up and make it melted, and you can get it in crystalline form, and its crystal structure is orthorhombic, and as soon as it is coming out, it is quenched in a bath, and it results in a gelled fiber, so it is kind of a squishy, uh, liquidy kind of a form. And uh, as it is coming out, then you remove the remaining solvent, and it is drawn at a temperature close to the melting point of polyethylene, which is approximately 120 degrees centigrade. And then you can also pull it at a slightly elevated temperature so that you get uniform diameters and things like that. So polyethylene fibers are obtained under trade names of Spectra and Dyneema. Spectra is made by, it used to be made by Allied Signal in Phoenix. I think there could be other places. And Dyneema is the European equivalent of polyethylene. It is made by a company called DSM Somos. It's got pretty low specific gravity, very light, and it floats in water. And the good properties are it has got very good abrasion resistance and excellent chemical and electrical resistance. But the disadvantages are that it cannot be dyed and it cannot be bleached or sterilized. And the other reason is that it's got pretty low melting point of 120 degrees centigrade. So this material can be used for making lightweight products, including rope and cordage, etc. Okay. Aramids are rigid rod, what are called rigid rod polymer fibers. And they are pretty much, they produce what are called known as Kevlar in trade name. It is made, it's an aromatic polyamide, not imide, polyamide, polyphenylene terephthalamide. Um, DuPont also makes another kind of polymer fiber called polyphenylene isothalamide, which is obtained under the name Nomex. And Nomex is what you use in the case of high fire resistance for and in firefighters suites, etc. Okay, so let me do one more. You can also have nylon, etc. And aramid is a manufactured fiber. It's a polyamide in which at least 85% of the amide linkages are attached directly to the two aromatic rings. So these have some benefits, but they are not, obviously they are not as good as carbon fibers.